When a scientist, engineer, or economist talks about exponential increase or decrease or geometric increase or decrease or alternatively increasing at constant rates, say 10%, she is thinking of an exponential function. An exponential function is kind of like the ultimate refinement of geometric sequences. Let's take an example. So suppose we looked at a geometric sequence that included the numbers 5 to the minus 2 or 1/25, 5 to the minus 1, 1/5, 5 to the 0, which is 1, 5 squared, 25, etc. It could go on in both directions. And we wanted to include the half powers. So let me just remind you what 5 to the 1/2 is. When your computer computes 5 to the 1/2, it finds the unique positive number y such that y squared is equal to 5. That turns out to be a rational number, and it's approximately 2.236. Once we know this, we can include the half powers in this geometric sequence. So the refinement could be 5 to the minus 2, 5 to the minus 3 over 2 now, 5 to the minus 1, 5 to the minus a half, 5 to the 0, 5 to the half, etc. It could go on in both directions. And then what we can do is we could include the cubic roots. We could keep going and going, include all rational numbers in this manner, and then by limiting even irrational numbers. And this brings us to the exponential function, which is our main object of interest here. Given positive number b, which is a base, 5 for example, above, the function f of x is equal to b to the x is called the exponential function. It has domain all numbers. So because we've gone through this limiting process, we've even included irrational, so you can take b to the anything, b to the pi if you want, b to the minus pi squared if you want. It's all possible. The range is positive. When you take a look at any of these numbers, 5 to the minus 3 over 2, 5 to the 5 over 2, whatever, they're all positive numbers. In general, as we'll see by graphing, it will include all positive numbers with one exception, and that's when the base is 1. You take 1 to the anything, you just get 1 back. So the range then is 0 to infinity, this open interval, if b is not 1, and just the single number 1 when b is 1. Now it's important to note that x to the b is not the same as b to the x. The former is just a power function, and the latter is this exponential function, what we're talking about. They're very different objects. Which brings us to the properties of the exponential function. So we'll give these properties and then give an example which would help us compute this refinement of this geometric sequence. So the first property says that b to the x plus y is equal to b to the x times b to the y. So the exponential function at x plus y is equal to the exponential function at x times the exponential function at y. Let's use this to compute 5 to the 3 over 2. 3 over 2 is 1 plus a half, and then by the property as 5 times 5 to the 1/2. Well, 5 to the 1/2 we just determined was 2.236, so we're left as 5 times 2.236, which is approximately 11.18. Next property that we have is b to the y minus x is equal to b to the y over b to the x. And in particular, if you take y is equal to 0, you'd have b to the minus x is 1 over b to the x. And if we then take b as 5, we have 5 to the minus x is equal to 1 over 5 to the x. So 5 to the minus 3 over 2 is 1 over 11.18, which is approximately 0.089. And 5 to the minus 1/2 similarly is 0.45. The next property is that b to the x to the y, so you take your exponential function b to the x and then raise that yet again to the power y. Well, that's equal to the exponential function at b to the x times y. So how could we use this to fill in our table to come up with what 5 to the x looks like and also what 1/5 to the x looks like? Well, what we could do is we could take 1/5 to the x, and then 1/5 is just 5 to the minus 1, which is just reciprocal. And so we could take y to be minus 1. And so the formula then gives us 5 to the minus 1 to the x is equal to 5 to the minus x. And so what this means then is that 1/5 to the x is equal to 5 to the minus x. And this means that 1/5 to the x and 5 to the x are reflections of each other in the y-axis. You just substitute x with minus x. And the last property, which we won't need here, so we won't give an example, is a times b, where both a and b are legitimate bases, so they're positive numbers. All to the x is equal to a to the x times b to the x. And so we can now use these examples that we just came up with to fill in this table to give us an idea what 5 to the x looks like. What we can do is we can start off by anything to the 0 is equal to 1, so we have 1s along this column. And then 1 to the anything is 1, so we have 1s along as well. And then we could just write the base, so 5 to the 1 just gives you 5 back, b to the 1 just gives you the base back, so you can write in the 5 to a half, 1/5. And then the base squared is just 25, 4, 1/4, 1/25. The base to the minus 1 is just a reciprocal, so we have a fifth, a half, 2, 5. And the minus 2 is just the reciprocal of the square, so 1/25, a quarter, 4, and 25. And now we're just left with these other elements in this row. However, we've actually already computed them. So the first thing we computed was 5 to the 1/2, and so we can write that in here as 2.24. And then the next thing that we computed, 5 to the 3/2, and that was 11.2, so we can write that in here. Then the next thing that we calculated was 5 to the minus 3/2, which was 0.09 from here. And finally, 5 to the minus a half is 0.45 from here. And then the next thing that we can do is we can note by this mirror imaging that the exponential function 1/5 the x is the mirror image of 5 to the x in the y-axis. Well, what we can do is we can just copy numbers from base 5 down to base 1/5, but for the negative x value. So we take the value when x is 3/2 in base 5, which gives us the value 11.2, and we copy that down to base 1/5, but put it in for minus 3/2. Then we can copy the 2.24 down and across to the 2.24 there. Similarly, the 0.45 for minus a half will in base 5 will correspond to 0.45 for positive a half in base 1/5, and then we copy the 0.09 down and across as well. Repeat the object for base 2, and then note that the numbers that are given in decimal are just approximate, and the numbers that aren't are exact. And now what we can do is we can go and we can plot the points of each one of these. So let's take the first row, and we can plot these points in base 5. So we can start off and we have 5 to the minus 2, 5 to the minus 3/2, 5 to the minus 1, etc. We get these points here. If we had included more and more points, what we would have is we'd just be filling up this red curve here, which corresponds to 5 to the x. Do the same thing for 2 to the x, and we get these points here. And if we had included more numbers, we would have got this blue curve here, which is 2 to the x. And then to get 1/5 to the x and a half to the x, we just note that these are reflections. And so what we can do is just take the mirror image of 5 to the x about the y-axis, and we get 1/5 to the x. Same thing for 1/2 to the x, it's just the mirror image of 2 to the x. We can check by putting these points on, which correspond to the last two rows in this table. And then finally what we can do is we can just draw the straight line for 1 to the x, and we have an example of what exponential functions look like, at least around x is equal to 0. And what we can see is an important point. When the base is greater than 1, which is the case of 2 to the x and 5 to the x, this is a strictly increasing function, so they pass the horizontal line test. If you drew a horizontal line, it would only intersect either one of these once. The case where the base is less than a half, these are decreasing functions. They're just the mirror images. They'll also pass a horizontal line test. The case where b is equal to 1, of course, that's just always 1. It can't pass a horizontal line because the horizontal line y is equal to 1 intersects with that everywhere. Now, this brings us to our last point, and that's the natural exponential function. There is a unique exponential function with base greater than 1 that intersects this line x plus 1 just once. So we've drawn this in here. And if we zoom in, what we see that 5 to the x intersects y is equal to x plus 1 at x is 0, but also for a negative number. And 2 to the x intersects at 0, but also for a positive number. Neither of these intersect this line once only. They both intersect twice. But there is a unique exponential function that intersects just once when x is equal to 0. This is the unique exponential function that has tangent line at the point 0, 1 of 1. And that's going to be very important for later when we do derivatives. The base for this exponential function is the Euler number. It's an irrational number, perhaps only second in fame to pi, and its value is 2.718 approximately. And if we let base be this Euler number e, it's either written as e to the x, or because of its real importance, it's also given the label exp of x. In conclusion, we defined the exponential function as ultimately refined versions of geometric sequences. We concluded that the domain of the exponential function is everything, all real numbers. The range is positive numbers, and when the base is 1, it's restricted just to the single number 1. Otherwise, it's all positive numbers. We also came up with the 4 most important properties of the exponential function. And we showed that these functions are increasing when the base is strictly greater than 1 and decreasing when the base is strictly less than 1. And then finally, we introduced the special exponential function, the natural exponential function, and stated that its base is called the Euler number.